Okay. As a reminder, on Unit 3, I have uploaded a document right at the top of the module that outlines all of the reactions that we're covering in this unit. It outlines them based on two sections. One section I'm calling alcohols and phenols. We already kind of talked about the acidity of those groups. And then the other section is ethers and epoxides. And you'll notice actually that when it comes to alcohols versus ethers and epoxides, there's a lot more to say about alcohols alone. There's just kind of a longer list of reactions there. But I've also broken them down into two categories: previously seen reactions and new reactions. So we are doing a review. We're reviewing reactions we've already seen. If you guys have the document that I've handed out, this is also uploaded. Unfortunately, I wasn't smart enough when I made the first one. So this organometallics and alcohols synthesis, and then this new alcohols and epoxide synthesis. We're going to actually switch from the old one to the new one and then come back to the old one to fill in some of the material. It's not going to be complete one entirely and then the other. And that's the part I'm not the most happy about. But this is where we are right now. We're on this flow chart here. We had gotten to oxymercuration reduction. The next reaction for us to consider was another hydration reaction with the alkene. What I need here is first borane. Second, I need aqueous basic aqueous basic hydrogen peroxide. A basic aqueous solution of hydrogen peroxide. Oxymercuration reduction actually uses this reducing agent, sodium borohydride. We're going to talk more about sodium borohydride today. And then hydroboration oxidation uses an oxidizing agent in the second step. Can you guys tell me what the oxidizing agent is? Water, sodium hydroxide, or hydrogen peroxide? If you had to guess. Hydrogen peroxides are oxidizing agent. Yep. What we get here is regio-specific, regio-selective. This is an anti-Markovnikov hydration, so I can get the less substituted alcohol out of this reaction. The other reactions that we learned about that we were reviewing, something seems wrong. I've got too many slots. The last reaction from alkene addition reactions that we learned was this diol addition. We can use osmium tetroxide, or we can use potassium permanganate, KMnO4, cold. This doesn't just give us an alcohol, so it's not just hydration. Both of these processes give us vicinal diol. That term vicinal, what does it mean? Adjacent to. There's another term, not vicinal. There's another term that means on the same carbon, twins. Geminal. Vinyl is when it's attached to an alkene carbon. For instance, this would be like a vinyl isopropyl group. Yeah, isopropyl connect to the alkene. Geminal, vicinal, vinyl. All regiochemistry terms. And I think I messed up, and I added an extra arrow here, but we don't have another alkene addition reaction that makes an alcohol. Correct me if I'm wrong on that, but I think that I messed up. There were a couple of other reactions that we have already seen before. Sorry, that's it. For instance, we can do SN1 and SN2 reactions to make alcohols. Here I can take something like methyl iodide, react it with water, and I can get methanol as a product. But it doesn't need to be water. It could also be sodium hydroxide. But if I wanted to take something like tert butyl chloride and make an alcohol, this must be done with water, cannot be done with sodium hydroxide. In the first reaction where I'm doing substitution, is this SN1 or SN2, or does it depend on the reagent? Oftentimes it does depend on the reagent. Water runs SN1 preferentially, where hydroxide runs SN2 preferentially. But on a methyl carbon, the carbocation intermediate is so unstable, and the amount of steric strain is very, very low. So it's actually easier for either of these to do SN2 than to do SN1, whereas on a tertiary carbon, it flips. Carbocation stability, very high, but steric strain, also very high. So hydroxide won't run SN2 here. Hydroxide will run E2. I can't use hydroxide to substitute on a tertiary carbon. I have to use a weak nucleophile so that it runs by SN1. And then the last way that we saw to make an alcohol was actually the way that we saw how to make a phenol. We called it NAS, but it's similar to SN1 and SN2 in that it's nucleophilic substitution. So we can call this SNAR. Just like before, we need an aryl halide to be substituted, otherwise nothing happens. Can I work with water to do this substitution? Think back to the unit test you guys just had recently. Will water run this substitution? Remember the mechanism of NAS. A pi bond breaks in the aromatic ring. Aromaticity breaks in the aromatic ring. Is it easy to break aromaticity? No. Is water good enough at sharing its electrons that it can break aromaticity? No. So hydroxide is the only reagent that can be used to make an alcohol here. The halogen is substituted, and now I have a phenol. Again, hydroxide, NaOH, equivalent things. If you see NaOH, I want you to think of it as OH minus. That Na is there as an ion, it's not doing anything. This is the most recent way to make an alcohol that we've seen, but these are all ways that we've seen to make alcohols. Any questions on them?
Do hydroxides come off of ionic bonds versus covalent bonds act differently?
There is no hydroxide on a covalent bond. I think that's the best answer. If OH is bonded to something, it's not hydroxide, which is an ion. All right. You know what? I lied. We are going to finish this. This is where we're going next. We're looking at new reactions to synthesize alcohols. These were all previously seen reactions to synthesize alcohols. This is what we're going to see now. You'll notice on this sheet that I have, underneath the hexagon that we didn't even get to use completely, I've got all these different arrows. Written a little bit confusingly. My goal is to demonstrate how several different precursors can all lead to the same product with the same reagent. So this entire thing can actually be classified as reduction of carbonyls. So a little bit of background. In order to reduce carbonyls, we need a reducing agent. And we will have two types of reducing agents. We have a strong reducing agent, and we have a mild reducing agent. Our strong reducing agent is a compound called LAH, which stands for lithium aluminum hydride. I want you to hear that word at the end. Hydride. What is that? You've worked with hydride before. H minus, negatively charged hydrogen ion. That's what hydride is. The structure of LAH is a lithium ion balancing AlH4 minus. So you can write out its chemical formula. If you don't like to use LAH, you can write LiAlH4. It is a source of H minus. What does that tell you about the electronegativity difference between H and Al?
Al is lower?
Yep. H owns the electrons, takes them away from Al. So we're not going to look at mechanisms here, but if we were to look at mechanisms, it would look something like this. Hydrogen takes electrons away from aluminum and shares them with the carbonyl. You can see how by adding a hydrogen to the carbonyl carbon, I'll create an alcohol. No, I don't, though. What I actually create is this complex. Not great if you're trying to get to an alcohol, but add some water, an aqueous workup, and you provide a source of protons. Our mild reducing agent is NaBH4, sodium borohydride. Notice in the name, hydride shows up again. This is another source of H minus. Where did we see sodium borohydride before? Hydroboration. Nope, sorry. Oxymercuration reduction. We use sodium borohydride as what? As our reducing agent, and that's what we're using it for again. Can somebody rationalize for me why lithium aluminum hydride is a strong reducing agent while lithium borohydride is a more moderate a weaker reducing agent.
Boron has a higher or closer electronegativity to hydrogen than Al.
Exactly.
Is this on the sheet yet?
No, sorry. Just a little bit of background. Boron is in the same family as aluminum. It's higher up. Boron has a stronger electronegativity than aluminum. So between hydrogen trying to take electrons from boron and aluminum, hydrogen can take electrons from aluminum more easily. Thus, it reduces more strongly. Hydrogen can't take electrons from boron quite as easily, so it reduces a little less strongly. This is very useful for us, and we're going to show the two ways that these are done. And then, both require aqueous workup. We're going to show an aqueous workup as a second step H3O+. First LAH, second H3O+. First NaBH4, second H3O+. A small caveat. Sometimes sodium borohydride is written with methanol and no aqueous workup. So if you see this on your homework, just understand that's kind of replacing the aqueous workup. I am going to show you exactly how I want you to send it back to me. First NaBH4, second H3O+. But if you do give me NaBH4 with methanol, it's correct, so I'm not going to mark it wrong. You just won't see it as my version of showing it. All right, on the left-hand side of this image, we've got 5 different things that are all reacting with the same thing to give us this compound. Someone name that compound for me? Ethanol. And then at the bottom of this diagram, I've got one more thing going to this alcohol. What's the name of that alcohol? Isopropyl alcohol, isopropanol. Any other names? 2-propanol. And we're going to introduce the same reagent to all of these. First, LAH. Second, H3O+. First, LAH. Then, aqueous workup. You know, some instructors, they think aqueous workups are just so redundant. They actually say, assume all aqueous workups. Don't write them, just assume them. But you know what happens when you assume? Makes an ass out of you and me. My high school chemistry teacher told me that. So I'd rather you guys recognize that it is meaningful that we have an aqueous workup. It can't be done without it. Sorry, one more time. Can you spot the difference between these two alcohols? Or could you name the difference between these two? Good. One is primary, one is secondary. There are a lot of ways to get to a primary alcohol, but there are fewer ways to get to a secondary alcohol. Actually, to get to the secondary alcohol, we have to start with a ketone. When ketones are reduced, you can kind of think of a ketone as a secondary carbonyl. The carbonyl carbon is bonded to 2 other carbons. So when I add a hydrogen there, I don't change the number of carbons that are bonded. All right, now this sequence up here, it's going to feel a little bit odd, but the reason I'm doing it the way I am is because we're going to keep all of the same functional groups here in the same sequence on the right-hand side. At the top, we're going to put acetic acid, ethanoic acid. notice the 2-carbon chain gets reduced down to a 2-carbon alcohol. The carboxylic acid has been reduced.
Where does it go?
It's all in the aqueous workup. On the second line, we're going to show ethyl acetate or ethyl ethanoate. This actually has two carbon chains, and it specifically produces two carbon alcohols. We're going to come back and touch on a special feature of those esters when they get reduced. Does this make enough sense? All of these form ethanol. This one also forms a second equivalent of ethanol. In the middle here, we'll have acid chloride, a 2-carbon chain. This is ethanoyl chloride. So the 2-carbon chain in all of these carbonyls gets reduced to that 2-carbon alcohol. And then again, basically a primary carbonyl because it's only attached to one carbon. A primary carbonyl because it's attached to one carbon. Primary carbonyl. Then we're going to have, you know what? I don't think it really matters, but I did mean to have aldehyde up here and the acid chloride beneath it. So this was meant to be aldehyde, acid chloride. They're not in a specific order, and if you look on the right-hand side, it's these two positions that stay the same. Lastly, on this long connection, anhydride. This is acetic anhydride or ethanoic anhydride. Once again, this also produces a second equivalence of ethanol. Do you recognize all of your functional groups? Because if you don't, now is the time to keep reviewing them. Get back into finding flashcards, get back into studying your functional groups, because these carbonyls will make up the entire second half of the semester. And it's important to have a good grasp on them. On the left, primary carbonyls, on the top, primary carbonyls, and on the bottom are one and only secondary carbonyls. These are ways of making primary alcohols and secondary alcohols. So before we move on to the right-hand side, what if I wanted to get to methyl alcohol, which is not a primary carbon? Could I start from a ketone? No, because the carbon of methyl alcohol isn't attached to any other carbons, and ketones have to have carbons on either side. I can't even start from acetaldehyde or ethanal. What I can start with are things like formic acid, formate groups, formaldehyde, formal chloride. All of these groups can be reduced. Oops, I can't even draw a line. Because they're just 1-carbon carbonyls. So you can get methyl alcohol, primary alcohol, secondary alcohol by reduction of these carbonyls. I also want to hint at some nomenclature that I just mentioned. Formic acid, formate, formaldehyde, formal chloride. When we use this prefix form, we're talking about a 1-carbon carbonyl. And when we use the prefix acid, acetic acid, acetate, acetaldehyde, acetyl chloride, acetic anhydride. Acetic, acete, is giving us a prefix for the 2-carbon carbonyl. Acetyl, 2 carbon carbonyl, formal, 1 carbon carbonyl. All right, and then another fun tangent here. Esters always give primary alcohol plus what I like to call a variable alcohol. In this diagram, I showed you an ester that has 2 equivalent carbon chains. Both of them get reduced to alcohols. But esters don't need to have 2 equivalent carbon chains. Also, esters don't have to be linear. Cyclic esters are called lactones. And lactones, like this, can have always a primary position and this variable position. What is the substitution of my variable position here? Not quaternary, tertiary. It's a tertiary ester linkage. The carbon is bonded to 3 other carbons. So when this is run with LAH and an aqueous workup, first LAH, then H3O+, I get 2 alcohols. 1 alcohol is primary, and 1 alcohol, in this case, will be tertiary, and their R groups connect. So this will give me a diol. In this case, it gives me 1,5 hexadiol. 5-methyl 1,5-hexadiol. Yeah. Do you see the positions? Here's that primary alcohol that was originally the carbonyl carbon, and here's my variable alcohol. In this case, my tertiary alcohol. It's a fun side quest that esters can do that none of the other groups can do. And I think you can see why, right? The aldehyde, always primary. The carboxylic acid, always primary. Acid chloride, always primary. Anhydrides, always primary. But the ester gets another carbon chain where you can change things up. All right, question on that?
Different mechanism for 4 of those 5?
We're not going to look at the mechanism. If you are curious the mechanism of reduction, take a look at the screen. Google Translate will give you this little overview. What we see here is hydrogen attacks the carbonyl carbon, creates some sort of complex with the oxygen, and then in the aqueous workup, more protons are added so that the actual oxygen gets hydrogens. So they all have the same mechanism, but it is true that some of these groups need more equivalences of the reducing agent. But your reducing agent is always in excess.
So boron takes one of the pi bonds of the oxygen, forms a bond to the oxygen, and then the hydrogen can come in.
The hydrogen comes in first. You'll even notice here, hydrogen comes in. They're saying at the same time that the oxygen bonds with boron. Although
To the carbon.
Hydrogen bonds to the carbon first. Yes. The OH hydrogen comes in the aqueous workup. Yep. I don't see my eraser. Am I blind? No, it's not just me, right? All right. On to the second side. If you guys would copy copy these same chemicals down on the right-hand side. And over the arrow, I know there's a lot more arrows. So I guess over all of the arrows, place the mild reducing agent. You said you needed something up there? It's good. Can you tell me which functional groups are inert to the mild reducing agent? Anybody? Carboxylic acid is inert to the mild reducing agent. NaBH4 with aqueous workup gives us, oh, what's NR? No reaction. Nothing happens. Maybe some acid-base chemistry, to be honest, but at the end of the aqueous workup, it looks like nothing has happened. Our ester reacted with NaBH4 and then with an aqueous workup. What happens? Nothing. No reaction occurs. Esters and carboxylic acids, the partial positive on that carbon is not strong enough to accept electrons from the reducing agent. And remember, this is a reducing agent that doesn't give electrons quite as readily. All right, then I've got two functional groups that have the same effect when reacted with sodium borohydride and an aqueous workup. And remember, here, I meant to have the aldehyde on top and the acid chloride on the bottom, but it really doesn't matter. These both give the same product as before, the primary alcohol. And to be fair, the acid anhydride gives the same product as well, but this time with a bit of a twist. The acid anhydride last time gave me two equivalences of the primary alcohol, but this time the acid anhydride gives me my alcohol plus carboxylic acid. Okay, we know that carboxylic acids cannot be reduced with sodium borohydride. So this actually tells us something about the mechanism of LAH reduction. LAH takes the anhydride and reduces one of the carbonyls into an alcohol, leaving the other carbonyl with the oxygen as a carboxylate, a deprotonated carboxylic acid. And then the reducing agent reduces the carboxylate in the same way that it reduces the carboxylic acid. We know that must be part of the mechanism because here, sodium borohydride reduces one of the carbonyls into the alcohol, which must kick off an equivalence of an acid. And the carboxylic acid, or the carboxylate, can't be reduced with NaBH4. So it gets kicked out as a byproduct to the reaction. That's why I have it shown on your table as a separate thing, because it's unique from the other two in that it has its own byproduct. It's similar to the two above it in that it does give us the desired product, but it's different in that it gives us a new byproduct as well. Killian, you had a question?
Does it only get It only can start the second step because it's an acidic solution, or because does it get the hydrogen from the NaBH4?
There are two hydrogens. I don't know if you've realized that. There are two hydrogens that are coming to the compound. One of the hydrogens comes from NHBH4 going to the carbonyl carbon, and the other hydrogen comes from the H3O+. So this black hydrogen was already present. This orange hydrogen came from reduction, and this green hydrogen comes from the aqueous workup. Reduction. Is this an addition reaction, elimination reaction, or substitution reaction? Sorry? Addition. Pi bond is consumed. Two atoms are added across the pi bond. In this case, they're both hydrogens. They come in different steps. One hydrogen comes in the reduction. One hydrogen comes in the aqueous workup. So down here I showed how if I can split up my anhydride into these two groups, I can actually clarify a little bit better about where these groups are coming from. And that's the same thing that happens with my ester up above. The black equivalence is already shown, now this orange equivalence. And now I can do the same thing here, where my byproduct is just 1/2 of the anhydride. Lastly, with NaBH4 as a reducing agent, I can also form secondary alcohols from ketones. All right, let's do a quick application of this. If you would please grab the second sheet that I gave you today. This one's uploaded on Canvas as alcohols and epoxides synthesis. And I actually want you guys to come down to the bottom. We're just going to look at this bottom reaction on the left-hand side. Notice how across to the right, you're shown a product, but there's no reagent. I want you to add a reagent there. And then coming down, you're given a reagent, but you're not shown a product. I want you to show the product there. Let's take about 5 minutes to fill in the reagent and show the product. I'll come around and answer questions that you guys might have. So we filled out. Oh, did you give up the last sheet? Oh, no. Oh, thank you. We filled out this diagram with that material, and then some extra material that's not on here, and then this diagram with this. Okay. And right now we're just applying those reagents to these two conditions. All right, why don't you guys turn in towards each other. At this point, you know it or you know that you don't know it. So turn in with each other and see where you're stuck. See what you understand.
That was a short 5 minutes.
No, we're spending 5 minutes on it.
I say one right is sodium, but tetra. Shoot, I don't know what it's called. NaBH4.
Yeah.
The sodium's not the important. It's the BH4. Boring, I think he called it. What? Boring.
Oh. Aha. Idea. Oh no. Will it still be attached? Dude?
For the LAH,
No.
Shoot, I
You
don't
should
know.
have one ring in that product. 2 alcohols. 3 alcohols.
1, 2, 3, 4, 5. 1, 2,
Yep,
3, 4, 5.
exactly. Oh,
1, 2, 3, 4, 5.
1, 2. You mix that all together, you just ruin it all.
well, yeah.
So how do we know the reagents for the top reaction?
Oh, yeah.
What change do we see?
Which one is it? Where's it written?
Okay, ketone to alcohol and ester doesn't react. So what reagent allows my ketone to be reduced but not my ester? Well, it can't be LAH. Ketone is reduced, not my ester.
1, 2,
Selective oxidation.
1,
Oh, sorry. Selective reduction.
5, 6, 7. Alcohol. Oh, I'm missing a card.
You know what? I think you're missing a carbon.
I'm not good at like that kind of stuff.
Then just count,
Gives us the
map
right
them, number them. So on your starting material, count this as carbon 1,
It removes
2,
the
3,
LAH is
4,
the one
5,
that removes the carbon.
and 5 actually connects back to the original.
Dang, if we
Oh,
do
that was
something different on each side,
Yeah,
wouldn't we?
Yeah,
It
but
uses both the carbon and breaks the ring that has the ester.
Yes. No. No. This is just attached to the wrong position.
is the so like the variable, does that also could it also include another primary?
Yes.
Oh.
It was here, right?
Oh, yeah.
It can be methyl, primary, secondary, tertiary.
Okay.
In fact, if this compound, I just put R because it's variable, but if I had made this methyl formate, methyl methanoate, I actually get 2 equivalences of methanol.
Oh, okay.
So esters can make methyl alcohols. They will always make a primary alcohol as well.
Okay.
Methyl, here if this was OCH3, then this would have been OCH3OH, CH3OH.
It slipped in my mind.
You can do anything you need to. What you should do is count your carbons to put the alcohol where it needs to be.
You know that.
Yes.
Okay.
And this is an ester.
So you have it.
And that's what you just said. But I think ester's always.
All right, let's go through it together.
This one's connected. So
In the top reaction,
Yeah.
what changes do you observe?
literally just like take them apart.
Yep.
And put it
Anybody? In the top reaction, what change do you observe?
1 carbonyl turns into an alcohol.
1 carbonyl is reduced, the other carbonyl is not. Can we be more specific? Ketone is reduced, ester is not. I need a mild reducing agent. This is selective reduction. I can reduce some of my carbonyls and not all of them. So for that top reaction, we need NaBH4 followed by H3O+. Check your line. Do you have 1 NaBH4, 2 H3O+? Because I take at least half a point out of 2 if you don't put those on your exams and on your unit tests. Typically, fill in a reagent is like 2 points, so a quarter of those 2 points, half a point, for not having the steps. Then I see that it's being reduced with LAH and H3O+. So here's my recommendation. We know the ring on the left stays intact and the ketone becomes an alcohol. Map your carbons on the right so that you can keep track of that ring opening. I should have done that here as well. Carbon 1, 2, 3, 4, 5, and then one of the methyl groups is 6. 1, 2, 3, 4, 5, 6. One way you can convince yourself this makes sense is that if you've got a 6-membered ring, a 6-membered lactone, the oxygen is one of those members. So there should be 5 carbons connecting it.
Lactone?
Yep, that's what cyclic ester is called. Here again, I have a 6-membered cyclic ester. So I should have 5 carbons connecting them. 1, 2, 3, 4, 5. And then I have the oxygen, which makes the 6th member of my 6-membered ring. Here's one way that mapping is better than just counting. Mapping is where you take these numbers on your product and you draw them on your starting material, where you should have noticed that carbons 2 and 3 are the 2 carbons shared by the rings. 2 and 3, 2 and 3. Rather than just rather than just counting, I've mapped them to make sure I haven't lost any atoms. I mapped them here as well. Okay. The other new way that we're looking at new ways to form alcohols is with acyl addition. Earlier we were looking at, I think I lost it already. We were looking at reduction of carbonyls. I guess we could have also called it acyl reduction. Yeah? And we said reduction was what type of reaction? Addition. So we can clarify this a little bit better by saying acyl addition with nucleophiles. Oh man, you know what? Hydride is a nucleophile. It's sharing its electrons. It's just not a typical nucleophile. These are your more typical nucleophiles. We're going to look at acyl addition with 2 things.
Is this the conjugate addition thing?
No, it's actually not the conjugate addition, but we already did get a sneak peek at this. So the first one we'll look at is with Grignard reagents. Do you remember which other reagent is interchangeable with Grignard? Not the cuprates. The organolithiums. In any of these examples where you see a Grignard, you could write it as an organolithium. If you see an organolithium, you could see it as a Grignard. So what I propose here is we show a number of different examples. Let's show how to make a primary alcohol. A primary alcohol, let's say ethanol again. In that product, which carbon is the carbonyl carbon? Yeah. We're synthesizing alcohols. We're doing it by Grignard acyl addition. I want to make a primary alcohol. Here it is. Which of those carbons was the carbonyl carbon of acyl addition? The alcohol carbon, yeah? And if what I've done is used a Grignard to create a carbon-carbon bond, that means that my carbonyl carbon was only attached to hydrogens before. A primary carbon as the product, primary alcohol as a product means a methyl carbonyl. This is methanal, formaldehyde. And what reagent do I need here? Well, I'm only adding a CH3 group. So I need methyl Grignard, CH3 MgBr, or methyl lithium, CH3Li. And I think we showed this last week how when the Grignard attacks the carbonyl, it creates an O-, not an alcohol. This requires an aqueous workup as well to protonate the carbonyl. Once again, I'm not interested in having you guys show the mechanisms for these components, but if you wanted to see what that acyl addition looks like, the methyl group takes the electrons out of the Grignard and breaks the carbonyl bond. That's what creates the O- that needs the aqueous workup to turn into an alcohol. Russ.
So just kind of preparing for the midterm.
Yeah.
How much of that are we going to be looking at mechanisms versus just knowing reagent of the reactions?
Good question. Actually, if you use these learning objective sheets, basically as a midterm review guide, only the reactions that I tell you to know mechanisms for will be fair game on the midterm. So that's EAS mechanisms, but not nitration and not sulfonation. NAS mechanisms, and then also acid catalyzed hydration, HX addition, halogenation, and halohydrin haloether addition from our OChem 1. It's more likely that you'll see EAS and NAS though. All right, what if I don't want a primary alcohol? What if I want a secondary alcohol? Let's say that the secondary alcohol I want to see is this. Those of you who didn't have lab last week, and those of you who did, you started with this material. It's called 1-phenylethanol. There's actually two different ways that we can get here. I'm going to show you both of those ways. But first of all, which of these carbons was the carbonyl carbon? The alcohol carbon was the carbonyl carbon. And I'm creating one of these carbonyl bonds, which means that my starting material, carbonyl, was not formaldehyde, but was an aldehyde. Here, I can show benzaldehyde reacting again with a methyl organometallic followed by an aqueous workup. You want to map your carbons: phenyl, carbonyl, methyl, phenyl, carbonyl, methyl. How else could I have synthesized this same alcohol? I can flip which carbon-carbon bond I created. So my starting material will be ethanal, acetaldehyde, or acetaldehyde, where I already have methyl carbonyl. And what I need to introduce is a phenyl organometallic. The benzene ring is bonded directly to the metal. If you have a secondary alcohol, you have two ways of synthesizing it using acyl addition. Two different carbon-carbon bonds. All right, are you guys tracking for what we're going to show here on the tertiary alcohol? I want you guys to give me 3 different ways to form this tertiary alcohol. They're all going to be organometallic with an aqueous workup. Please work together. If you'd like to give it a shot on your own, then I'm going to call you in to work together in just a little bit. Do you want a hint before you even get started?
Yeah.
Primary alcohols always have formaldehyde as a precursor. Secondary alcohols always have an aldehyde as a precursor. So your precursor here must be what type of functional group? A secondary carbonyl, the ketone. All of your starting materials here have a ketone in them.
You can do it with organolithiums or grignards, but if you start a reaction with a grignard and you want to add another carbon group, can you finish it with organolithiums?
You're saying if you want to do multiple reactions?
Yeah.
Yeah. If you do one reaction, it doesn't.
Do you have to like decant the magnesium out? Or
Yeah.
you have
Well,
to,
during the aqueous workup, the magnesium gets oxidized.
what does it turn into?
Magnesium ion.
So do you have to get rid of it?
All right, here's tip number 2. Identify your carbonyl carbon and identify the 3 bonds going to it, and selectively break one of those bonds off and make that group an organometallic. Draw the ketone that results. Great. Just building a template, right? Good start. That's an alkene. It's like a carbon-carbon double bond. Not meant to be like a wedge or anything.
Oh, sorry, yeah. It's the way I've been drawing it.
Okay, that's good. So you know you're going to have a ketone in each of the starting materials. The question is, what will the ketone look like, and what carbon group will you add? So let's look at that tertiary alcohol, and notice how there's a methyl coming down.
No,
Just like last
not
time, we
the
looked
right
at
number.
secondary alcohol, and notice there's a methyl. So I could actually take off that tertiary carbon methyl carbon bond.
Oh, and then that would be where the organometallic.
So methyl organometallic, like methyl lithium, and then I'd have a ketone at that position instead of the alcohol.
Oh, okay.
So actually, almost like this,
But it would just have
but no methyl. The methyl would be added in the reagent.
Oh, okay. Thank you.
Mm-hmm. How are you feeling? Okay. So here we added a methyl group to make that secondary alcohol. Do the same thing here. We'll add this methyl group, which means our starting material, if we consider adding the methyl group here, or I guess you were actually adding it here already. Our starting material is less that methyl group with a ketone there instead of an alcohol. Do you want to try discussion? Same carbon chain. So the ketone at that position repeat with the other 3 sides? Or the other 2 sides? Good. Great. Well, you've already cut 2 of the bonds, so now you just have to cut the last bond. You're almost there. Oh, let's do that. No, I'm just kidding. You got too many carbons here, actually. Here's carbon 1, 2, attacks 3. And then you've got 1, 2, 3 attacks 3. So instead of 3, you actually want that. Mm-hmm. Yes, great. And now we do that again, but instead of cutting this group off, we cut this group off. And then this group off. 3 different carbon chains, 3 different new reagents added. Anybody want to add theirs, or should I just put them on? Put them on? Yeah, I want to see this. That's a good start. You know what reagent you're going to add then. So let's start.
Can I try one?
No, actually, I think I'm going to go through. Sorry. Let's start with this CH3 that's coming to the tertiary alcohol. The tertiary alcohol will be a ketone starting material. I can try to highlight this is what I'm going to break. And I'm going to come up to this one. I want this methyl carbon to attack the ketone. So I'm going to add methyl lithium and an aqueous workup. That's how I'll create that carbon-carbon bond. But what does the carbonyl look like before it? Well, the rest of the carbon chain remains unchanged. And at the alcohol carbon, I have a carbonyl. There's my acyl addition. Now I rinse and repeat. I want to create this carbon-carbon bond, which means my carbon chain is now the alkene, the carbonyl carbon, and the methyl group. Different ketone starting material. The reagent I need to add has carbon 1, 2, 2 attacks the carbonyl. So I want this to be something like this. Carbon 1, 2, and carbon 2 attacks the carbonyl, followed by an aqueous workup. True or false? My last product will have an alkene in the starting material. False. The only bond I haven't shown forming in this acyl addition is between the carbonyl carbon and the alkene. And it's that bond right there that I want to make, which means that my organometallic reagent looks like this. The alkene bonded directly to the organometallic. Again, carbon 1, 2, 2 attacks 3. Carbon 1, 2, 2 attacks 3. My starting material, that's methyl, carbonyl, ethyl. Methyl, carbonyl, ethyl.
The Li could be MGBR.
Correct. Tertiary alcohols have 3 different ways to synthesize. How can I synthesize a quaternary alcohol? Cannot. Why? Quaternary alcohols don't exist. You can't have a carbon bonded to 4 carbons and an alcohol. All right, let's take a quick break before we look at reactions with alcohols, ethers, and epoxides.
You can't.
Let's do like 5 minutes or less.
You can't get drunk on carbon.
Try.
You want to go fish packet? of age for kids to be introduced to horror movies?
Never.
We're watching a horror movie. ACS students. Kids horror movie.
I think horror. Okay. I think horror is bad. Bad bubblegum. I needed that. I needed that word space.
Wow.
How much more do you have to write down?
Questions.
You already have it. Have you gone to the?
I might have just been wrong, but I was just verifying we do that.
Yeah.
Okay.
Let me prove it to you though. Under the midterm module. Oh, it's not visible.
That's
Oh, wait, this is... That's not the one I wanted to give you guys either. Thank you, Brett. I'm sorry. I swear that was something I did like. Oh, it's right there. So I added them. Oh. I just never actually put them in. And I think I always forget to mention this too. I'll be unlocking all of your unit test questions for you guys to review. I think kind of the downside of it though is that I can't unlock it until Tuesday morning next week because you're, you know, you're still taking it until Monday night. Oh, that needed to get done for a long time.
I think you might have posted that with class.
You opened it?
Yeah. It looks like the midterm we had last semester.
Dang. Yeah, it literally says 2310. And you know what? I think that's why I had those on here is because I uploaded that up here. Oh my god. Tired of this, Grandpa.
Did you object? The bad.
Yeah, it seems like I probably just never uploaded them.
New one. The one where they speak in Spanish?
No, it's just where I volunteer at.
Oh, yeah. Where do you volunteer?
It's a free clinic up in Ogden. What is it?
Or do any other U students go there?
It's mostly people from Weaver State.
Is it a
Killian, are you done with that side of the board?
Completely free.
No, John, I need to have any questions.
What's the question you have?
Questions.
Yeah, hang in there.
How are you?
Doing pretty good.
Why what?
Need another tissue.
Started a new job, so they gave me
You need a tissue?
well, they gave me
No.
fresh, and then I
The board needs a tissue.
I ran out of space.
Totally medical. Pretty cool.
You have a question?
I made
Yeah.
the maternal fetal medicine clinic.
There you go, Brett.
Yeah, I just started yesterday and just training all day.
Today's the last.
And I have one more day of full training.
Yeah, unfortunately.
You
I
don't
wanted
want
it to be Thursday, but
It never happened.
fall break and all that.
Yeah, it'll be cool. I'm excited for it.
See you.
We started actually start.
Okay, good luck on your unit test.
Training videos.
How do you know what?
Yeah.
I have an ester. Esters get reduced to 2 alcohols. One is always a primary alcohol. The other, it depends on the substitution.
How are we supposed to figure that out?
Because you're given that you have LAH, and you know that esters get reduced to 2 alcohols. Because I showed you that they make 2 alcohols. And then I gave you more information. I told you esters always go to 2 alcohols. You don't have this down?
No, I do.
Okay, great.
So you can do this right after that because this goes to BH3.
No. These are not the same reaction.
But you have the BH4, doesn't it?
Actually, BH4 creates like a quad complex. It reacts 4 different times.
You talked about with the 4 oxygens, but the 4 gets broken.
All 4 of those hydrogens get donated away. We're looking at this new spiral diagram. That is a heptagonal orientation. We've got 7 reactions to go through here. And a number of these are previously seen reactions. So we just looked at synthesis of alcohols. What we're looking at now is reactions with alcohols. And we're going to start from this 2-butanol. Well, one of the first things that we learned we could do with alcohols was run halohydrin addition. So if our alcohol here was subjected to elemental bromine and ethylene, then I can get this haloether product. Notice how the 2 carbons of ethylene, 1, 2, get added across, once with a bromine, once with an ether. And that ether group comes from my alcohol. If you'd like to see the presence of the alcohol a little bit more easily, color coordinated there. So alcohols are used in alkene addition reactions. They're used to make ethers. We also said that alcohols can be reacted with things like PBr3, SOCl2, and I'm going to put HX because we can use HCl, HBr. PBr3 substitutes my alcohol for a bromine. Thionyl chloride, SOCl2, substitutes for a chlorine. And then based on the nature of my X, my alcohol is substituted for a halogen there as well. OChem1, correct? Reactions we've seen already, correct? And now I want to see that I can get my 7 sides. Boy, how did they do this? So we saw alcohols can be substituted into alkyl halides. We also saw that alcohols can be substituted into these pseudo-halides. we add something like tosyl chloride, we'll abbreviate it as TSCl, and the alcohol here actually behaves as the nucleophile. It substitutes the Cl on the tosyl chloride. We call it a pseudo-halide because it behaves like a halogen, but it's not a halogen. And of course, we can run dehydration on our alcohols. H2SO4. This is most often an E1 elimination, which means it has a carbocation intermediate, so it will take whatever configuration puts the alkene at the lowest energy. Those are all of our previously seen reactions. The rest of these what we're learning now. All right, so this one's kind of interesting. I have not seen a name for it before, so I tried naming it. Acid catalyzed alcoholysis. Similar to acid catalyzed hydration, except this time you're using an alcohol, not water, and you make an ether, not an alcohol. If you take an alkene, let's take propene, and you react with acid catalyzed etherification, if you will. It's not hydration, but it's etherification. You're going to make an ether, and this ether, once again, it forms on the more substituted carbon. This is me mapping my carbons of my alkene and mapping them down here. It's just like acid catalyzed hydration, except I'm not using water, I'm using an alcohol, and I don't end up with an alcohol, I end up with an ether. It's so similar, we should have taught it in OChem 1. It's not that different. That's okay? Once again, if you're a little confused about where the alcohol has gone, we can color coordinate this sec-butyl group up here to being that of the carbon chain of the alcohol. Then we have acid catalyzed esterification. We're going to spend a lot more time on the mechanism here in our next unit. We're not going to spend any time on it here. Starting materials are carboxylic acid with acid. And the product is an ester. Once again, that ester chain is the alcohol's carbon chain. This is almost like the reverse of reducing the carbonyl. If I took this carbonyl and I reduced it, one of the products I would get is this alcohol. I wouldn't get a carboxylic acid. Wow, and it seems like I added an extra one again. So I don't have anything else to put into that other arrow. Because these other ones, we're going to need to write them out a little bit differently. So, sorry again. There's one more that is oxidation of vicinal diols. I'm going to show you that this vicinal diol is a bit different on the two sides. One side is a tertiary alcohol, one side is a secondary alcohol. The oxidation that we're running here is with per-iotic acid. That's HiO4. It's really fun to write out periodic because it's spelt periodic, but pronounced periodic. This does a really interesting thing. It cleaves the carbon-carbon bond between the two alcohols. If I map my carbons, 1 through 4, I'll find that carbons 2 and 3 get cut off from each other. And this example illustrates how tertiary alcohols get cleaved into ketones, whereas secondary, primary alcohols get cleaved into carbonyls. All right, now we've got a big category, which is oxidation of alcohols. Once again, we have 3 main oxidizers that we're going to be working with here. Our strong oxidizer is chromic acid. And we're going to write chromic acid as CrO3 H2SO4. What have we used chromic acid for already?
Was it in the zinc? Just the with zinc?
No, it wasn't with zinc. It was in that same section. Benzylic oxidation. Taking a benzylic hydrogen on some carbon group and turning that whole carbon group into a benzoic acid group. It's already been a strong oxidizer. Then we have a mild oxidizer. This is pyridinium chlorochromate. But we're going to abbreviate this as PCC. Pyridinium is a conjugate acid. It's an organic acid. It's that aromatic ring with nitrogen that's protonated. And it's balancing chlorochromate. You'll actually notice chlorochromate, chromic acid, they both have some amount of chromium in them. But the pyridine and the chlorine that are part of PCC, they moderate the effects of pyridinium, of the chromic acid. They make it more of a mild oxidizer. And then we have a selective oxidizer. This is allylic and benzylic oxidizer. Manganese dioxide, which we will write as MnO2. All right, some examples. If we start with methanol, our smallest alcohol, and we react with chromic acid, we initially get a dicarboxylic acid. This is methane dicarboxylic acid, also known as something you learn in gym chem, something that's in your soda, also a little bit in your blood. Carbonic acid. Carbonic acid is famously not stable, which means that if this forms, it decomposes into water and carbon dioxide. And that's what you actually harvest. One thing that we're not looking at there we're going to come back to understand later is that this oxidation takes methanol first to formaldehyde. And then it oxidizes formaldehyde into formic acid. And then it oxidizes formic acid into carbonic acid. So it's actually a three-step reduction, or excuse me, oxidation. Oh, but you already knew that. Because there are 3 hydrogens on carbon that need to be pulled off in order to get to this stage. Formaldehyde, formic acid, carbonic acid.
Is chromic acid CrO3 in a very acidic solution?
This?
Yeah.
Chromic acid is very acidic, yeah.
So chromic acid is a acidic chromate?
So chromic acid is formed when you have chromium trioxide and sulfuric acid.
Is that chromate?
No, chromium trioxide. Chromate is CrO4 minus. If I take methanol and I react it with PCC, I get formaldehyde. Notice the mild oxidation. It's removed one of the 3 hydrogens and stopped. What happens when methanol is reacted with MnO2? Is that benzylic? Is it allylic? No reaction. Look at primary alcohols as our starting material. Let's say I've got phenylmethanol, and I react this with our strong oxidizer, chromic acid. By the way, there are places where you will see chromic acid called Jones reagent. How much does that help you understand what's going on? It's one of the worst.
Because Jones is not even a memorable name like the other ones.
I actually can never remember if Jones was chromic acid or potassium permanganate. So I think chromic acid is better. Plus, when you remember this as chromic acid, you have a better connection between your 2 major types of oxidizers. What functional group do you think I'll get at the end here? Look at the functional group we got when we oxidized methanol or formaldehyde. I should get a carboxylic acid. 2 hydrogens at that carbon have been removed. That carbon has been oxidized. How does this change when I use PCC instead? Do I still get a carboxylic acid? Here, I get benzaldehyde. Good. 1 of those 2 hydrogens has been removed.
Can you draw PCC?
I'll show it to you. Can't remember how many oxygens are there. Three oxygens, 1 chlorine.
Oh, it's an ion. Oh, that's just pyridine.
It's pyridinium. I believe your learning objectives sheet gives this to you. But we're looking at MnO2 giving us aldehydes or ketones, which means MnO2 is not only selective, it's also mild. Here, will MnO2 give me benzoic acid, benzaldehyde, or no reaction? Benzaldehyde. It can't be a ketone because it's a primary alcohol, but it is a benzylic alcohol. Benzyl alcohol is another name for this. All right, the The last one to look at is from secondary alcohols. And here we actually have less to consider. If I react with, how do I want to show this? If I react this with chromic acid and if I react this with PCC, I get the exact same outcome. Both of these are secondary alcohols. Chromic acid, despite being strong, it's not going to break any of these bonds. So chromic acid takes both secondary alcohols into ketones. PCC takes both secondary alcohols into ketones. PCC is only good at oxidizing one hydrogen. All it has is one hydrogen. This same reagent, when reacted with MnO2, can you predict the product?
Does it make a ring?
It's not going to make a ring. It will just make one ketone. One alcohol is allylic, one alcohol is not. One ketone, one alcohol. Selective oxidizer.
This isn't on the sheet at all.
This is not on the sheet at all. No. Okay, that was where I wanted to get through at the end of today, and now we have to keep going because we don't have Thursday's class. Man, and I knew that was coming and I forgot. So these are reactions that we need to see with ethers and epoxides. I actually am not going to spend any time on this first part. This is reactions that produce ethers. Halo ether addition, we just looked at that. SN1, SN2 with alcohols and alkoxides. Acid catalyzed etherification, we just looked at that as well. In fact, the only one that I really want to highlight here is the Williamson ether synthesis, which is so funny to me. You know that's a guy, Williamson ether.
His name was Ether?
I was going to say producing ethers, but I want to say consistent synthesis of ethers. See previously. And then also this Williamson ether synthesis. So here's what Williamson's reaction does. Take an alcohol, okay? ROH. You react it with a strong base, sodium hydride, and you isolate the alkoxide that comes from that. And then, to make an ether, you react that alkoxide with an alkyl halide. Does that feel new to you? What does that feel like? Does that not feel like SN2 with NaOR? Because that's exactly what it is. Williamson ether synthesis is simply the production of the alkoxide. In OChem 1, you saw how you can just take an alkoxide and run substitution. In OChem 2, you just see how to make the alkoxide. But of course, this can all be summarized. So you can say, start with an alcohol, add a strong base, and follow that with the alkyl halide to show the substitution. There is some preference on the alkyl halide. You want this to be a less substituted alkyl halide. That was true back in OChem 1. This works best with methyl, primary, and there's competition at secondary alkyl halides. You get some elimination as well. To be honest, I don't think it's worth our time to show a specific example because that's OChem 1 review. There's really nothing new there. Reactions with ethers. We already saw how. Oh. Well, actually, I need to fix that. I say there are previously seen reactions, but there are not. You've not seen a reaction where an ether is in the starting material, so that's a typo. What we can see, though, is SN1 in acidic conditions, HX. Here's the general rundown. Let's say I have tert-butyl ether. So I've got tert-butyl on both groups. If I add one equivalence of HBr, I will substitute one side of that ether. I get tert-butanol, and I get tert-butyl bromide. I take the ether, in acidic conditions, I protonate it, and I can split that ether apart. And the halogen goes to one side. But it's more often that you run this in excess of your acid, and in which case, the alcohol that you form also gets substituted into an alkyl halide. So you get two equivalences of alkyl halide. There is a difference with aromatic ethers. Aromatic carbons cannot go through substitution by SN1. So let's take anisole. Anisole is methoxybenzene. If I subject methoxybenzene to an excess amount of hydrochloric acid, I can still substitute and I can break apart the ether. But despite being in excess, I won't get two alkyl halides. My aromatic ether can only be decomposed into a phenol plus whatever other alkyl halide is going to be formed. In this case, methyl chloride. Does that track? These reactions require SN1. SN1 can't happen on the aromatic ring, so the aromatic ring never loses its oxygen. Is that me? Is it you? What was that noise?
Oh, you guys probably made that noise, but that sounded like it was the room.
Yeah. Anyways. All right. That's it for ethers. Do you know ethers, the brilliant thing about ethers, they're pretty inert. That's why we use ethers as solvents for a lot of reactions, because they're not going to do anything. There's not a lot going on here. But now we want to look at synthesis of epoxides. Remember that epoxides are almost ethers. except for the fact that the two R groups are connected to each other. That creates a lot of angle strain, which means that ethers are opened a lot more easily than most other ethers are. Epoxides are much more reactive. The first way that we saw to synthesize ethers was with MCPBA. I'm sorry, epoxides. So we take an alkene, we react with metachloroperoxybenzoic acid. And I say this, but I wanted to say it differently. MCPBA is the most common peroxy acid, but this is really much more commonly used MCPBA, but it could be any peroxy acid. The other way that we can synthesize them is with SN2 from a halohydrin product. And I say SN2, but it's going to look a little bit like elimination, a little bit like substitution, but it does require being SN2. The stereochemistry is specific. Let's say that I have this halohydrin. Notice that the two groups are vicinal to each other. They're on adjacent carbons. Notice that their stereochemistry is anti. One is wedged, one is dashed. That's required. And if I introduce here a strong base, I'm essentially running Williamson ether synthesis. I'll deprotonate the oxygen, and the oxygen will kick over to substitute the halogen. If I were to draw stereochemistry here, would it be both wedges or both dashed? It can't be one wedge, one dash, because that means that the oxygen is both above and below the bonds, which doesn't make sense. But since the oxygen was wedged before, it must still be wedged. Although, to be fair, that's a meso compound, so you can flip it over and it's also both dashed. But you don't have to draw stereochemistry quite as often because epoxides have to be on one side or the other. Those are our two ways. Pretty straightforward. All right, this is where you can use the middle part of this sheet. Here I've got reactions with epoxides, and I want you to notice that there are two unique conditions here. One of those conditions is if your epoxide is in basic conditions. And I put this box here as a transition state. I'm going to show you the transition state in the reaction. If epoxides are run in acidic conditions, then the epoxides become protonated. I just realized that I drew my epoxide opposite of how it looks on yours, so I apologize for that. But I do want to point out this really odd part of my protonated epoxide. Do you see that? What's weird about that? It's not a perfect little triangle anymore, is it? I did that intentionally. I did that manually. I've stretched one of the bonds. Can you tell me something about which bond I've stretched?
The one opposite of the methyl.
I stretched the bond to the more substituted carbon. Why would I do that? Well, which of those carbons would be able to take on that positive charge more easily? The more substituted carbon. So by stretching that bond, I am distributing part of that partial positive into that carbon. And that's going to explain for us how these groups will react. In basic conditions, if I have a nucleophile like nuc minus, I will always attack at the less substituted position That's going to give me this intermediate. That should feel like SN2. That should feel like nucleophile goes for the less substituted carbon, the least amount of steric strain. And the product that I get here at the end, well, typically we'll need some sort of aqueous workup, but we're often looking to get an alcohol after we open an epoxide. In acidic conditions, my nucleophile isn't nuc minus. We're in acidic conditions. So I'm just going to show a lone pair. It's a neutral compound more often than not. And because this bond is already stretched, this is the easiest bond to break. So my transition state looks like this. I attack at the more substituted position. Basic conditions, less substituted attack. Acidic conditions, more substituted attack. So what are the most common nucleophiles that we see? We can see water or hydroxide. That gives us the difference between acidic conditions and basic conditions. If I react with water or hydroxide, I actually can't tell the difference. Because either way, my epoxide gets opened into a diol. We could pay attention to which oxygen was brought during which step by isotopically labeling these carbons. I should have titled this something like opening this into a diol. I can also open this into an ether and an alcohol. And this is where the regiochemistry actually plays a difference. If I react this with ROH in acid as opposed to RO minus, I get different products. In acidic conditions, my alcohol nucleophile will attach at the more substituted position. Whereas in basic conditions, my nucleophile attacks at the less substituted position. What's the relationship between those two products? Structural isomers. That's one of the key pieces of epoxide synthesis, structural isomerism. Which structural isomer are you looking for? That tells you which conditions you need to use, whether you need to have acid or whether you need to have nucleophilic. I hate to say this, but I've run out of time, and I realized there was something I missed earlier. I showed you guys acyl addition of carbonyls. I showed you guys acyl addition of carbonyls with alkyl halides. I forgot to show you acyl addition of carbonyls with cyanide. It works all the same, except you get a cyano group and an alcohol off of the same carbon. I'm pretty sure you have a homework problem that shows you this. The other thing I haven't been able to show you is that with peroxides, I've labeled what can be done in acidic, what can be done in basic. Notice that you've got water, hydroxide, alcohol, alkoxide, hydrogen cyanide, cyanide. But what you don't have an analogy of for organometallics is organometallics in acidic conditions. Organometallics cannot exist in acidic conditions. So organometallics open epoxides always in basic or nucleophilic conditions. You cannot have it any other way. I think because I was planning on having class with you guys on Thursday, I think what I'm going to do is record a video of myself solving these multi-step synthesis problems, and I'll post it for you guys to watch. And that should help you prepare for your unit test this weekend and your midterm next week. If you have questions on these, you want to send them to me, I'd be happy to review. You have written work for this weekend as well, correct? Your written work is multi-step synthesis. That's why you need to practice applying all of these reactions in a sequence. Count your carbons, brainstorm, work forward and backwards. All right, guys. Have a good weekend. Enjoy your fall break.
Midterm's on Thursday, right?
Midterm is a week from Thursday. That's correct.
You'll review.
Tuesday is a review period. Yeah, so Tuesday, come with questions. Because I don't know what you guys want to review the most. So if you guys don't bring questions, I'll just put on Veritasium and we'll have a cool day.
So what midterm are we? Is it also from unit 1 or just the new content?
It will be Unit 1, but as you kind of have seen, a lot of Unit 1 came back today. So, yes, there will be things about like spectroscopy, but you'll get the spectroscopy correlation tables. There will be things about OChem 1 reagents, OChem 1 products.
But like more of the context of these.
It will be largely applied to aromatics and this kind of stuff, yeah.
Are you looking at
Thank you.
You're welcome.
what we got?